Hello everyone, I'm recording here this lecture for the February 6th lecture, which will be affected because of my conference travels. This lecture is not going to be part of the midterm that is on the 8th. So now let me go to the material here so I can start the lecture. Let's just pause this. Okay, so we'll talk here about how to measure distances. And we basically kind of started this in the lab part, where we were talking about if we have 2 points, A, for example, and B. Another point here, this is A and B. Need to double click here, and B. How to measure the distance between these 2 points. And we said there are going to be a couple of ways to do that, but the most important thing we said, when we report distances, our distances in surveying are the horizontal distances. So we have to be careful with that. So what are the different methods here? Pacing, we did introduce pacing in the labs. We can use odometers. We are going to use EDMs as part of our total stations, and EDMs will be integrated in the total stations. So we are not really going to use them by themselves. I show you how to use GPS, for example, satellite positioning systems, chaining, a very old technique, but still very important to understand because it was the base for all the surveys that were done a few years ago. Actually, a few centuries ago, in 1600, 1700. Laser scanners, we don't really use them to measure distances, but the product, which is a point cloud, a 3D point cloud, could be used to measure distances. We also have a technique called stadia or tachometry. That's a technique we will be showing. We don't really use substance bars anymore, and taping is the main focus of this class here. So make sure when you measure that you are referring your measurements to the horizontal distance, unless otherwise required. As I described here, let me go to the whiteboard. This is the distance that we need to record. Again, which method do we use? It depends. It depends on the accuracy, on the time that you are going to require. A lot of factors do make or are required. A lot of factors here are going to be considered. Okay, with pacing, we did our pacing in the labs. Most people have a pace distance, or what we call the step length, of about 2 to 3 feet. And it really varies if you are going uphill or downhill. A good way, as we did in our labs here, is to define 2 points, and then between these 2 points here, measure the distance with a tape, and then you pace a couple of times, and then you take the average number of paces and define your average step length here. That's a good way to calibrate your step length. Pacing is very low accuracy for sure. It's the lowest precision, but again, we can use it to get some rough estimate. Its precision is 1/50, 1/100 of the measured distance. What does this mean? That's something important we need to understand in surveying here, the relative precision. So let me clear the board here. Let's assume I have this line here, and I measure the line between the 2 points, or the distance between the 2 points, and the distance that I found was 300 feet. If my precision is 1 to 50, that means every 50 feet, I will be off plus or minus 1 foot. In other words, in the 300 feet, this could be off by 300 divided by 50 times the 1. So 300 divided by the 50 multiplied by 1. So it will be off by 6 feet. So my distance could be 294, 295, all the way to 305, 306. I don't know. No one can really say it's plus or minus. That's what we call the plus or minus. So it's plus or minus 6 feet. You see where the 6 feet came from. How about if my survey has a relative precision of 1 to 100? That means that I'm going to be off plus or minus the 300 divided by the 100, which is 3, much more precise, and so on. And I'll give you a couple more examples when we go to taping. So this here is the relative precision. So back to the PowerPoint here. So pacing will be plus or minus 1 to 50 or 1 to 100. Another technique we use is to use a measuring wheel. We don't really use it for precise measurements, but we can use it to get rough estimates for lengths. Distances that are measured with a measuring wheel are precise up to 1 to 100 or 1 to 200. So if you think about it the same way, 1 to 200 for the same distance here, if it's 1 to 200, and I'm really repeating this because it's a very important concept in surveying. So 1 to 200 means you are going to be off by plus or minus 1.5 foot. Is it exactly 1.5 foot? No one can say that. No one can really know how precise the measurement is, but it's up to 1.5 foot plus or minus both sides. It's a random error. It's an error that no one can predict its value. Okay, now we go back here to our slides and we see what other techniques do we have. We have the chaining. Chaining was used in the 16th century and the 17th century, all the way to maybe early 19th century, when the public land surveying system was being laid out. So the public land surveying system, which covers the entire 30 southern and western states, was laid down using, most of it for sure, was laid down using a chain. Now let me make this here a little bit bigger, and then I'm going to show you. This is the chain here. It has 100 links. So if you counted these links, they are 100 links. This is the actual chain. And after every 10 links, there is a mark here. That mark, as you see here, is different from the first 10 links, the second 10 links, the third 10 links, the fourth, the fifth, and then it goes all the way back here. So when you are measuring, if you are measuring using the whole thing, it's 60, as it shows here, it's 66 feet here. But the first 10 will give you the first tenth of the chain. So you divide the 66 by 10, so that means it's going to be the first 10 is 6.6 feet, and then so on until you get the whole thing. The handle here is part of the measurement, because you see the first link here is a little short, so to compensate for the length of the handle here. That's how this was designed. Unfortunately, we don't have one here. These are the actual marks here. You see how they look here. So 100 links, and they are connected by these rings here. EDMs, we'll talk much more about EDMs, but the idea is to use electromagnetic waves, or to use something called the EM signals, and then the signal is emitted from a transmitter here, and it goes all the way, travel until it hits a reflector, and then comes back to the to the source or to the transmitter here. So we'll talk about it in more details later. GPS does not really measure distances, but it measures coordinates, and then from the coordinates you can start defining your distance. So to show you an example here, let's take a case like a 2D case. So you have XY, you have 2 points, and again, I can't really show you the Z. I can, but I would like to focus here. And then if I give you XY of this point and XY of this point, and let's call these 2 points A and B. So this is XA, YA, XB, YB. So what is the distance between the 2 points here? What is the distance? You just use your Pythagorean theorem or just use your geometry here. The distance is the square root of the differences in X, and you square that, and the differences plus the differences in Y. So if you have the coordinates, you can easily find the differences in X, you can easily find the differences in Y, and then square them and square root the sum, you get the distance. How about if I have an extra dimension here, Z? Then each point will have an extra coordinate. So we'll have ZA, we'll have YA, ZB, and then you just add the square root of the difference in Z. You just add the square of the difference in Z squared. So that's how this works. So that's the only way to do it with the GPS. And the equation is here and the coordinates are showing here. Laser scanners, they do not measure distances. However, they do generate what we call a point cloud. And through the point cloud, you will have thousands and millions of points. You can identify your point and then determine distances. We do not use laser beams. We do not use laser beams. So why don't we use these laser measuring tools? First of all, they have a very limited range. They are not supposed to be surveying tools. That's why they have limited range. And also, it's very difficult to align them horizontal here. So that's why these are not surveying measuring tools here. Taping will be the one we are going to describe and I'm going to show in this lecture. I'm going to pause here and finish this part just to make sure it is recording and everything is correct. Then I'm going to do the second part after that.
Okay, so let's talk a little bit about taping. And we've done taping in our labs. We have different type of tape lengths. The one we use in surveying are the 100-foot tape and the 200 feet tape. We have both. These are the main ones. Just to remind you that our tapes are marked in feet, tenths of a foot, and hundredths of a foot. Another thing also to know is the precision of these tapes are 1 to 2,000 to 1 to 5,000. Okay, so let's here see the board. What does that mean? You have a tape, you measure the distance. This distance is, let's say, 3,800 feet. Little difficult here to use the mouse. Anyway, when we have a 3,800 feet here, and let's say our precision is 1 to 1,000, that's the relative precision. What does that mean for our length? If we follow the same procedure before, every 1,000 foot will have a 1 foot plus or minus. every 1,000 meter will have a 1 meter plus or minus, and so on. So our 38, I could have just used the text, but that's fine. 1,000 divided by 3,800, sorry, divided by the 1,000 will give us, times the 1, will give us 3.8 feet. And remember, that's plus or minus. We cannot guarantee it's always going to be plus, nor it's always going to be minus. No one knows. It's between, our error is going to be between, and let me type here better. Our error is going to be between positive 3.8 feet and negative 3.8 feet. No one knows. If I know the value of the error, I will just add it or subtract it to the 3,800. But I don't really know. No one really knows what the value of the error is here. No one really knows what is the value of the error here. So that's why it's between these two. That's why it's a random error. No one can predict its value. So from this here, what we can conclude is we have to be careful with the relative precision. Now, let me ask you this. Let me clear. And let's say I have two lines, or I have two surveyors. One that has a 1 to 1,000 relative precision versus one that has 1 to 2,000 relative precision. Which one is more precise? For sure, this one. Why? Because every 2,000 feet, he's going to be off at most a foot. The other one, every 1,000 feet, he's going to be off at most a foot. So the bigger this number, because this number is like a ratio. If you look at this value here, we can type it as 1 over 2,000. So the bigger the denominator here, the better the accuracy or the precision. Sorry, when I talk about precision. So the bigger the denominator here, the bigger the precision. Okay. Let's go back to my slides here. This is what we have for taping. We usually will have two people, one that holds the 0, one that holds the 100. Why did I put this? This is very simple here, but I put this for a particular reason here. Let me go back to my whiteboard here, which is very helpful. If you have a tape, particularly with steel tapes, be careful where the 0 starts. Usually this is the tape, this is the ring here, and then you have the first foot, the second foot, the third foot, and so on. So this is 1, 2, 3 foot. Be careful, is the 0 at the beginning of the tape, or does it start from the ring? Is the ring part of the tape? Some tapes, they leave the first foot for the decimal part. So some tapes starts from here, 0, 1, 2, and then you get this part. The very first part is what we call the decimal part here. So you get marks for the tenths and the hundredths. So what exactly are you using? Be very careful with that. Okay. With tapes, we have accessories. You probably have seen them. We'll talk about them in a little bit. We have different types of tapes. We have the cloth tape. We are not using them anymore because they tangle and twist very easily, shrink and expand much more than steel tapes. We have metallic tapes. We don't also use these ones. We use the fiberglass in most of the labs. They are more durable and washable. They expand and shrink for sure much more than the steel tapes, but they are okay for our labs here. The most common surveying tape is the steel tape. That's the tape that most surveyors will use. And that one, this is a picture of it here. is made of what we call flat steel bands or cables here. Its expansion and shrinkage is much more better or less than the other types. It doesn't tingle or kink as the other ones. We have something called the invert tapes, which is made from special nickel steel alloys here. We use these ones in more precise geodetic. These ones are used in geodetics. Let me put it. Surveys. The good thing about them, they don't expand or shrink as the steel tapes. Their thermal expansion, which determine how much they will expand or shrink, is much lower than the steel tapes. So that's why we use them if we need really, really very precise measurements. Right now, we use total stations, but still, why is this important? Because we had what we call the control points, like the benchmarks. We have horizontal control points, points of known XYs or northing easting. And these points were monumented in the 50s or before. They were monumented with these tapes. They were set with the invert tapes. So we need to understand how it worked if we would like to analyze and assess the old surveys. So maybe we can just say their importance is coming from using them in old surveys. If we would like to come and assess these surveys now, we need to be aware of them. Okay. Some accessories, chaining pins. We use them in our surveys to mark intermediate points. Hand levels, we didn't really use that. We don't often use it, but it's a small hand level here where you set it very close to the level. This is the hand level. And then you look through it and try to make sure your tape is leveled. Right now, we just eyeball it, so that's good for our labs. Tension handles, we do have these tension handles to apply tension. Why is tension important? I have to be careful here if I just didn't share the screen, otherwise you'll be looking at a different screen. I recorded this 2 times before that, and I forgot to share the screens on some of them, so that hopefully that wouldn't happen this time. Okay, tension, you have a tape like this, and then you pull it from one side and you pull it from the other side. Actually, don't pull it from the other side, we hold it from the other side. But for simplicity, let's assume you pull it from both sides. What will happen to the tape? The tape is going to deflect or sag. By applying the pressure here, let me use a different color here, by applying the pull at both sides, again, just for simplicity, let's apply the pull at both sides. What's going to happen here is the sag is for sure going to be much less, which means better accuracy. Okay, I don't want to do this. I want to go to share a new screen. Okay, this is what we call the tape clamp. So I was just talking about how we hold the tape. So at this end here, instead of having the tension handle here, we can use a tape clamp. That's nice. You can just hold the tape with a tape clamp here. I need to go to share. Okay, so I need to make sure I handle this correctly. So we use tape clamps here, just for the safety, because the tape is very sharp, the steel tape. We use pocket thermometers to measure the temperature if we are going to be applying temperature corrections or corrections for the change in temperature. I'll talk about this in a minute here. Range pulls. Let me describe the purpose of range pulls. Whiteboard. Okay. Clear or drawn. So let's assume here is point A, here is point B. I'm going to show a side view that looks like this. And then the top view, this is A, and this is B. Okay, and in the top view here, so let me write it down, side, low, top, right? So now you would like to tape between the 2 points. You start taping in this direction. But if you look at the top view here, if this distance is, let's say, 1,500 feet, you can't really get it at one point. You will not be able to get it from one tape. So what you need to do here is you need to break it down into segments of the 100 feet, and so on. I'm doing these lines on purpose, not aligned together. If you looked at the top view, the first one, this is AB, by the way, this is AB. Now let's put our tape. The first segment starts from here and let's say to here. And then the second segment goes from here maybe to here. You can't really align your tape exactly on the point because the point is not marked, or the line is not marked on the ground. If the line is marked on the ground, that's great, but that's very rare. So these 2 points, you can't see them from each other here. You can't really, if you stand it here at B, this is a person here, you can't really see A. So what we do here is we set the range pole high enough. We set a range pole very close to A, another one very close to B, and that helps you align the point, align your line. So when you're here, you can see A, but you can see, let me get another color here, you can see the top of the range pole here. So you know where A is. So instead of going all the way out of the line, you will be in the line. And then when you are somewhere at this place here, taping here, you can look all the way up and see where B is. So you can align your line better. Okay, let's go back to the, so that's why they are made that high. Plumb up, we've used plumb up. Why do we use plumb up? We use plumb up in this case, that's why I did it this way, because if the tape is here, I would like to make sure my starting point or ending point coincides with the point I am surveying to or from. This is just a demo. Let's see if it's going to work. If you are taping between 2 points here, you first set the range poles. Why didn't we use range poles outside? You see the engineering meadow is almost flat. I mean, it's not really flat, but the slope there is gentle, so you don't really need range poles there. But if you're in a mountain area and you're using a tape, then you need to do that. Okay, so we start from here. This is our first training pin. This is the other person here. And then he's going to move. This guy is going to move with the tape. And then he's going to set a training pin at 100 feet. And then we remove this one. This guy will take it. And then both will move until both guys are moving here. And then we set the other one. Now this person takes this training pin and then they both start moving and so on. So that's what we call the different segments or the different taping parts here. If you are taping on a sloping ground, make sure to use the plumb up. Otherwise, you get inclined or tilted distances here. Try to proceed from uphill, downhill. Okay, let's go to the board here. And let's clear it. Let's assume I'm taping on this hill here. Then I tape this way. I should be taping Oops. This way, which is more convenient. If you start taping this direction, by the end you come here, you're very tired and you might not be able to get the length correctly. And one more thing, when you tape down hell like this, you will be able to set your starting point here and then level it and then plumb it like this. It's much more difficult to do it here because then you plumb at the point on the ground. So it's much easier doing it this way. So just a convenient that we use in our practice. Okay. This is an example here. This is an example. If the slope is very big, if the slope is high, then we can break the tape. Instead of taping at hundreds, we tape 50s. So we take the slope. You see this person here, he's doing a 50. That's the rest of it. He's going to place a chaining pin and then do another 50 because the slope is, or the area is very steep, or the slope is very steep here. So that's much better to break the tape. That's why we call that's what we call breaking the tape, not physically breaking it, but we break the length segments here. Remember Pythagorean theorem, remember the trigs. If you are measuring horizontal and required to get the slope distance, if you happen to measure the slope distance, you have to put it down in the horizontal distance. But then the question is, how do we measure this angle? Well, you might then need to do a level. So think about now combining leveling and taping. You can, that's not the practice. Maybe I give you a question saying we taped on the level, on the tilted surface for any particular reason. We did have the difference in elevation. What will be the horizontal distance? Okay. Let me pause here. Just I'm going to stop and make sure everything is working, and then I'll come back with the remaining stuff. Okay, hopefully this will work. So far so good, no problems. I'm just making sure, do I need to do anything? Okay, so I'm recording now. So now we will talk about what type of errors can we expect when we use the tape. And I'm here highlighting 3 main errors, and then these are what we call systematic errors. We can, for systematic errors, we can define a physical modeling, meaning a mathematical formula. I can show you the formula, but they are not required, or the formulas, but they are not required for the class, and apply the formula to get the errors. Unlike when I talk later about random errors, non-systematic. I'll show you some of both, and then you will say, oh yes, that one we can for sure define it, that one we cannot. So let me start here with the incorrect length of the tape. Let me tell you the story, and on a whiteboard here, incorrect length of the tape. Here is the story. I purchased the tape from the store, and they told me the tape is 100-foot tape, 100.00. Then I went to 2 surveying monuments that are set to calibrate tapes. We have such things. And surveyed between the monuments and found the tape is not a 100-foot tape, but it's actually 100.02 feet, or maybe 99.99. So it's a little bit less or more than the 100-foot. Now, of course, I can't find it 90 feet or 99 even. It will be within a margin of few hundredths of a foot. I can't really return the tape. I mean, it's still usable if it's like plus or minus 3/100th of a foot. But the question is, can I use it? Yes, you can. Now I go and I survey a building. And let's say this building, I'm using the tape, and I got, with my tape, I measured this side to be 400 feet. I'm just using some exact numbers. And this side here to be 200 feet with this tape. That's using the tape. Oops. I'm going to tell you the question now. Let me get the blue here. Now I tell you, well, the tape is not actually 100. The tape is the I wanted to erase this here. The tape is not 100, but it's, for simplicity, 99.98 feet. So this is not really a 400, because the actual tape versus the nominal, we call this here the nominal length versus the actual length. The nominal length, the length that I believe it's a 400, but it's actually 99.98. So what will be the actual length of this building here? You think about it, this is what you did. You laid down the tape for 100 foot, and then another 100 foot, and then another 100 foot, and then another 100 foot. But each 100 was not really 100. Each 100 was 99.98. So in fact, this length is not really 400, but instead it's the 99.98 times 4, which will give you 399.92. You want to double check the math? I'm not sure if you'll be able to see my screen for the calculator, but I'm just using the calculator here. Yes, it's correct. Because this, I told you it's 100, but it's actually 99.98. This segment, I told you it's 100, but it's actually 99.98. So you lose 200ths, 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 200ths. So that's why it's 399.92. How about the 200 here? Well, the first one here, you laid down 100. The second one here, you laid down another 100. But this 100 wasn't actually 100, it was 99.98. The second one was also 99.98. So it turns out that your 200 is what? Think about it till I draw it here. If you want to do the math, you'll say, well, first 100 was 99.98. Second 100 is another 99.98. So in total, that's what? That's a 199.96. You lose, that's the actual length. You see how that works? This is the actual versus the nominal length. Hopefully that describes and illustrates the purpose and the concept here. Okay, back here. So that's the first one, the incorrect length. Now we go to the field temperature. You'll find it here. Is that tape really 100 foot? Okay, field temperature. These tapes, when they sell them to us, they tell us this. Why does it say move it? Let me double check that I'm sharing it. Okay, when I purchase a tape here, they say this tape is calibrated at a certain temperature. So let's say 30 degrees, 68 degrees Fahrenheit. So they measured this tape at 68 degrees Fahrenheit and it was 100.00 feet. Now you come and use it at 100 degrees Fahrenheit. And let's, for simplicity, assume you are measuring 100 foot. So is your measured distance here? You measured 100. Is it really 100 or less or more? What do you think? Let's think about it here. What happens is, because it's 100 feet, the tape is going to expand. So if this is the starting point, our tape is going to expand a little bit. So if the distance is 100 feet, you are going to get a less reading or a lower reading. Does that make sense? Let's repeat it in a different way. The tape is 100 foot. This is what tape is. But that's at 100 degrees Fahrenheit. Sorry, at 68 degrees Fahrenheit. When it expands, your 100 feet will be a little less. If that doesn't make sense, let's clear our drawing and get it a different way. I have 2 points. Where is the... Let's do a new share. Okay, here I am. Let's assume I have 2 points and they are exactly in the field in the Death Valley, 100 feet here. That's these 2 points, just happens to be exactly 100 feet. I gave you a tape. I told you this tape is, let's get another color here. I give you the tape. I told you this tape is 100.00 feet at 68 degrees Fahrenheit. You took it to this high temperature. What will happen to the tape? You start here when it's 100 degrees Fahrenheit, the tape expands a little bit. So the reading you will get will be a little bit less. I mean, maybe I'll give you some numbers, but it will be for sure a little bit less than the 100. If you went to a different place where it's, let's say, 20 degrees Fahrenheit, and you have a different line, but it happens to be, let's call it just for simplicity here, CD. What will happen to the tape at 20 degrees Fahrenheit? It's going to shrink a little bit. So it's not going to go all the way to the 100. It's going to be a little bit less. So your measured distance will be a little bit less. Hopefully that makes sense. So you have to be aware of that. The other one is sag. So if we come here, sag I think is simple to understand. You should have a tape that is like this, between, let's say, 2 points. You have point A, point B, but they happen to have a profile that looks like this. So you use the plumb bob here and here. But since you are putting the tape at a higher elevation, what's going to happen is it's going to sag. Hopefully I can get the sag with the mouse. So it's going to do like this here. Got it. Okay. It's going to deflect or sag because of the weight of the tape. And we can measure the weight and compute the sag. So with sag here, since you didn't really follow the shortest distance, which is a straight line, your reading is going to be a little bit more than what it should be because you are following the curve, not the shortest distance. So that's for the sag. A way to minimize the effect of sag is to put intermediate support. So when you put intermediate supports at different places, that should help you reduce the sag. If you want zero sags, then you lay it down on the ground. Now, I should maybe have paused for a second, but that's fine. Let's continue here. Going back to the incorrect length of the tape, that, as you see, could be positive or negative. You could have a tape, the 100-foot tape as 100.01 or 99.98. Field temperature, it could be more, let's say 100 degrees Fahrenheit, or it could be less, 20 degrees Fahrenheit. So your error or correction could be positive or negative. You don't know. It depends on the case. But for the sag, the reading is always going to be more. It's always going to be more than what should be. Always positive, which means we need to subtract the correction here. Okay, now other errors, what we call the non-systematic errors, alignment, for example. I shouldn't just go this way. I should go to share this and clear. Let's show the top view between A and B, 2 points. And then you have the 2 points here. And this is how the 2 points here. That's a top view. That's not. That is top view. Then you try to put the tape and align it. So no way you can get it exactly aligned. So maybe this is the first segment here. Goes a little bit out of the alignment. And then the next segment, maybe a little bit out of the alignment. And then the third segment, a little bit out of the alignment, and so on. That's the alignment error. Now, since you are not really following the shortest distance, which is the straight line, that is always going to give you a distance or a length that is greater than what it should be. If you really want to find the exact distance, then you have to find the angle here. These angles between the shortest distance and the line, but no one really do that because it's within the acceptable tolerance of the tape. But just to let you know, it's always going to be much more than what it should be, meaning you compute or you measure the line and your reading is always going to be higher or more than the actual line here. Okay. Do we go back? Improper plumbing. Let's take a look. You have point A, you have point B, but the side view looks something like this here. That's a side view. The one before was a top view. That's a side view. Use a plumb up. Let's use the arrow here. Use a plumb up. This is your point. This is your point. And then you have a plumb up here. Now the plumb up for sure will not coincide exactly with the point. It can come up a little bit in or out. No way you can get it exactly on the point. So you can't really say if the error or the line is going to be positive or negative. You can't say if you need to add or subtract. So that can cause you an error that's plus or minus, depending on whether you are in or out the line here. But that's how it looks like. Same thing here. You don't really know if your line is going to be in or out. Okay, another error. Incorrect reading. Well, that really, again, that's not really a random error. That's a mistake. That's a fatal mistake if you read the tape incorrectly. And if you are not just doing the estimates, if you are reading 11 instead of 1, boom, that's wrong. You need to redo the whole thing. Okay, so with this, I conclude this presentation. That's for February the 6th. I'm going to give you instructions if you have questions or if you need help. Thank you, and let's stop the recording from here. Let's see.